Hello and welcome to another episode of the Physics Corner, a series of videos in which we set up and solve introductory physics problems. I'm your host, Dr. Christopher Sorolla. In today's episode, we'll be looking at a car on a banked incline. So let's set up our situation. Imagine you're in a car driving down a road and the road has a curve. So this is a view from more or less above, if you will, showing the car at this particular moment going straight towards you. Notice that the curve of the incline, the curve of the road is pointing that direction. The center of the circle or the arc of the road is in that direction. This is a view from the side in which we see the car coming straight towards us. Here is the bank or the incline of the road itself, and the car again is pointing that way, or the direction of the center of the arc of the road is in that direction. So there's actually two things going on that are separate, right? There's the curve of the road itself, and there's an incline. So this is a view from the side, this is a view from above, to get that across. All right, so our question is this. Assuming that the curve is banked or inclined, at what speed must we be moving at in order to make this safely? More specifically, if there's no friction between the tires and the road surface, now that's not very realistic, but we'll do that in a separate episode. If there's no friction between the tires and the road, then the car at some particular speed will be either sliding upwards or sliding downhill. At one very specific speed, it will be stationary on the incline. It will neither slide up nor down. And that's what we're trying to find. So let's see what we can do with this. This is a forces problem, and therefore we set up a free body equation to solve for it. Also, Newton's second law, F equals ma, and one further twist, because this is a curve right here, that means that there is centripetal or center-seeking acceleration at play. Let's set up our free body diagram. So, as always, free body diagram, you can just simply write down a circle to stand for your original object. And now let's talk about the forces. Now, we're going to look at the situation of the car at this instant of time, right here, okay, where it's coming straight towards us. That means that the weight of the car, as always, is pointing straight down. We'll call that mg. And because the car is on a banked incline, the normal force, which points perpendicular to the bank, will be in that direction like this. Because there's no friction, we don't have a friction arrow to draw for that. We also do not have any others that we're going to worry about. We're not going to worry about, say, air drag or any other possible forces. Let's keep this simple. Okay, so that is our situation. All right, now, here's where it gets a little tricky. Now, if we were worried about the car sliding up or down the incline, you might think it would be best to choose coordinates that would, say, go down the incline and up like that. And we have done that in previous videos. But in this case, the acceleration, the centripetal acceleration, is pointing straight outwards like this towards the center of the circle of the road. And therefore, it's going to make most sense to keep our coordinates horizontal and vertical. In other words, we'll call positive x going like that and positive y like this. So in that case, now we need to adjust the normal force rather than the weight, which is something that we would have done in a previous video. So let's do that. So let's redraw our free body diagram to illustrate this. Weight is pointing straight down already, so that's not a problem. So what about normal force? There'll be a component of normal force going up this way and a component of normal force like that. If you look very carefully, this angle here is the same as the bank, and therefore this is the adjacent side, so this will be n times cosine theta there. And because this will be the opposite side, if you will, that will be n sine theta. And again, positive x going to the right, positive y going up. The reason to do this in this particular way is so that the motions are all in horizontal and vertical. Specifically, the center of the circle or circular arc of the road is a horizontal line. It's not tilted down the incline, it's horizontal. So let's keep it horizontal. That's why we're doing it this way. All right, so let's set up our equations. As usual, sometimes it's a little bit easier to set up equations in the y direction. Now, I'll use this lingo just to be a little bit different in case you've seen it this way. Summation of forces in the y direction. Sometimes I write F net, but let's do the summation signs for a change. just to be different. That will be n cosine theta going up and subtracting weight, mg, going downwards. And we're assuming, this is the whole point, after all, that the car is not going up or down, and therefore the acceleration in y will be 0. Okay. Now, looking ahead a little bit, that's going to imply that the normal force has kind of an interesting solution. The normal force will be mg divided by cosine theta, like that. All right. But getting ahead of ourselves. All right, let's try the forces in the x direction. Again, just to be a little different, summation of forces in the x direction, in case you've ever seen that version of this. All right, what are the forces in the x direction? Well, without friction, there's only one force, n sine theta. That's it. So, n sine theta. So there's not much of a summation. But if you don't have a summation, if you don't have any terms to subtract against each other, you can't cancel. Therefore, there must be a net acceleration, and so ma. More specifically, looking ahead again a little bit, because this is on a curve, the road itself is turned into an arc of circle, this must be centripetal acceleration, like that. Okay, and we'll bring that formula in soon enough. Okay, so first off, let's compare the two equations we've set up and see if we can solve for the centripetal acceleration. All right, so mass times centripetal acceleration equals m sine theta. But n from the first equation is this. So mg divided by cosine theta, sine theta like that. Or if you wish, let's move the parentheses around, and this is legit. You can do this. mg multiplied by sine divided by cosine. The reason I might want to bracket it this way is because sine divided by cosine is familiar to everybody as tangent. So we can just skip to the chase and call it mg tangent theta. And if you look carefully, mac here, mg tangent theta there, the mass is common to both, and so your acceleration is simply g tangent theta. Now that solution should look vaguely familiar. It's not identical, but it's similar to a case where we just had a box sitting on an inclined plane. But if you go back and look at that video or that particular problem, you'd find that acceleration is equal to g times sine of theta. And that's because it's a slightly different situation. We have centripetal acceleration here, and we have to worry about normal forces in a little bit different fashion. So, similar but not identical. All right, next step. How do we get speed out of this? Well, centripetal acceleration has a formula v squared divided by r, or the speed squared divided by the radius of the circle. Let's put that in. So v squared over r equals g tangent theta, like that. All right. So we're comparing this parts now. Let's see here. Let's move the r over. So we have v squared equals rg tangent theta. And finally then, v equals rg tangent theta square rooted, or if you prefer to the 1/2 power. Looks a little simpler like that. So this is our algebraic solution for this problem. All right, one more thing. Let's put in some numbers to see what it might look like. So v equals, we have r is 75 meters. G, we've rounded off to our usual 10 meters per second squared. And it's tangent of 10 degrees. And let's not forget, after all is said and done, to take the square root of all that. So calculate the inside here, get a number, take the square root. When you do that, you get a number of about 11.5 meters per second, or if you prefer, about 26 miles per hour. Now, interestingly enough, if the car is moving at exactly this speed here, then it will neither slide up or down the incline. If it's going faster than that speed, it will go up the incline. It'll tend to slide off the road. But if it's going slower than that speed, it will slide down the incline. So it's only at, this is kind of an interesting case, only at this specific speed does the car stay at the same height, if you will, along the incline. Other heights don't matter. All right, thank you for your attention. Technical support is given to us by Sydney Geltraw and Sophia Turner. Funding is from the University of Mississippi and the University of Southern Mississippi. Our video was made in Hattiesburg, Mississippi. I am your host, Dr. Christopher Cirola. Thank you for your attention, and clear skies, everybody.